Welcome back. This is section 11.4, Center of Gravity, which is section 10.1 in your book. Center of gravity and center of mass we're going to use as the same terms. It's slightly different. If you have more and more mass, you will have more and more of your own gravity. You will pull objects towards yourself. So every mass exerts a certain amount of gravity. Bigger masses exert more gravity. As soon as you are more massive, then what happens is that your gravity, it could be slightly different than your center of mass. Your center of mass is the average of all your weight. The center of gravity is where the gravitational pull comes to, or where it's pulled towards. So the Earth, the center of gravity would be at the very inside of the center of the Earth, since it's a sphere. But if you have different weights in different places, you might have a slightly different center of mass than center of gravity. If you're talking about a book or a pencil or a hammer and you're throwing it, please don't throw hammers, but if you do, your center of mass and your center of gravity is exactly the same. It's wherever the average weight is. So this slide gives you an example. The center of gravity in the Sears Tower, it's the tallest building in Chicago, is about a millimeter below the center of mass because the lower stories are pulled a little more strongly to the Earth's gravity than the upper stories. So where is the pull of gravity that's pulling on, in this case, the Earth? Well, it's slightly lower than the average of the mass because of its nearness. Remember that gravity has to do with how close something is. So the only time that you're going to get anything different of a center of mass and center of gravity is when you have something so huge that one side is close enough to the other mass that its gravity would attract more than the average mass would. If you throw an irregularly shaped object, like a board cleaner bottle, it's very possible that the center of gravity or the center of mass would be inside the bottle. But if you throw a very weird shaped object, like a boomerang, the center of gravity doesn't have to be actually inside the object itself. It is simply where it all tends to average or go to. So if you throw something and it wobbles around an external axis, say a boomerang would go around an axis that's outside of the boomerang, that's still very possible. Its center of gravity would simply be outside of the object. So let me show you an example with the solar system. The solar system has lots of mass in the planets. If you think of the entire system as one object, the sun is the most massive, and so the average is going to be closer to the sun. So you would have to balance, if you were going to balance the whole solar system, the center of gravity would be not in the sun or not in any of the planets, but outside the sun, but very, very close to the sun. It would be the same thing as if you were to balance a spoon on your hand. The balance part of that spoon would be closer to the bowl of the spoon than to the handle of the spoon because there's more mass in the bowl than in the handle. If you have a uniform object like a ball or a block, then your center of gravity absolutely will be inside the object. But if you have an irregular shaped object, like a chair, if you're throwing a chair and you've got all these different sticky out parts, the center of gravity could be outside the actual chair itself. Don't throw chairs. Here's the basic definition of the center of gravity. The weight of the entire yardstick behaves like it's concentrated at its center. So if you hold it at its center, it balances on both sides. You don't have any torque that's making it fall off of your finger, and you can hold that entire stick, even though it's a whole meter long, you can hold it on a couple millimeters of your finger, and it'll sit just fine. So if you are providing a support force here, all of the force of its weight is acting backwards to you in such a way that it's almost like all the weight is concentrated at a certain point. And as long as your support force is under that point, it's stable. It won't fall. If the support force is placed anywhere except the center of gravity, you're going to have a torque, and then it'll fall off your finger. So wherever you support something, if you were to put a nail in something and support it, its center of mass will always be under the support. Okay, so if you place it on something and it stands, the support force is underneath the support force is underneath the center of gravity. If it's suspending from something, if you hang it from a wire or from a string, it will always, its center of gravity will be always under the support. So if you were to take an irregularly shaped object that's not mathematically helpful, you simply would put a plumb bob and the center of gravity is always under the support. Do it for several places, and wherever they line up, that will be the center of gravity. I think it's in Kansas. This is what I was talking about before. The center of gravity in these objects are not in the object itself. It's as if the average of all the objects in this pot are in a place that there's no material in that pot, or in a chair, or in a cup, or in a boomerang. All of these ones, if you were to throw them, would pivot around this point, even though there's no material in that exact point. It's just the mathematical average of where all of the mass exists. Okay, are you smart? Where's the center of gravity of a donut? It's in the middle of the hole. The center of gravity in a donut is in the hole, or an inner tube, or a tire, or anything like that. Here's another question. Can an object have more than one center of gravity? Well, no. If it's a rigid object, if it's a stiff object, it will only have one center of gravity. If you have something that can change, like if you were to throw some water or throw some Play-Doh or something like that to where it could actually change shape while it's being thrown, if it's changing shape, then as soon as it has a new shape, it has a new center of gravity. But that's not two at the same time. At any one point, it's only going to have one center of gravity because it's essentially a mathematical average of where all of the matter concentrates. It's a concentration average. So last question, how is the center of gravity of an everyday object related to its center of mass? For an everyday object, they're identical. The center of mass is the center of gravity.